So good morning, everyone.
Good
Welcome back
morning,
to.
sir.
Yes, good morning, Suraj. Praneeth, welcome back.
Good morning, sir.
Very good morning. Surendra and Yashwant, welcome back.
Good morning, sir.
Yes. Good morning, Anish. Welcome back.
Good morning, sir.
Very good morning. So session will begin in few minutes. Okay, waiting for SAR's arrival. Okay, stay online. Good morning, sir.
Good morning, sir.
Very good morning, sir. Hope my voice is audible.
Yes, sir. Yes, sir. I
Okay,
was
sir.
doing some modification.
Fine,
Are,
fine, sir.
are you able to see the screen? No, right?
Let me share the screen, sir.
Huh.
Sorry, let me pass the control to you, then you can share it.
Huh.
Making you as a host, yes, you can accept and take the
Yes.
control. Yes.
Yeah. I think now the screen is visible, right?
Yes, sir. Visible, sir.
Yeah.
Yes.
Thank you.
Okay.
Yeah. Hello. Good morning, everybody. Am I audible? Hello. Good
Yes,
morning,
sir.
everybody. Yeah.
Yes, sir.
Yeah. Thank you. So today we'll begin a new subject, which is thermodynamics and its applications. Thermodynamics and its application. Let me discuss first about the GATE syllabus and the weightage of this subject, as well as the textbooks that you need to refer. And then I'll give some feel about the weightage. Like, it's very important in mechanical engineering. If you take the subjects list now, out of those subjects, I'll see like a one of the most weighted subject as thermodynamics and its applications. Let me give all those kind of numbers as well as the information. Yeah, coming to the syllabus, I'll divide this thermodynamics and its applications as two parts. One is fundamentals and basics. Fundamentals are basics. The second part is applications. The second part is applications. Coming to the syllabus perspective, the first part will deal as something like basics, assuming that we don't know anything about thermodynamics. We'll learn some fundamentals under the first part, which is basics. The second part is learning these basics or fundamentals. We'll see how to apply these things on real systems or real applications, like whatever we see around us in the nature. We'll see those things as second part, which is applications. So coming under basics, so the first chapter we'll see as very basic fundamentals. And then followed by a first law of thermodynamics, followed by a second law, and then followed by entropy, and then followed by availability, availability, and then finally I'll write here one more chapter, which is properties of pure substances. Properties of pure substances. And then thermodynamic relations. Thermodynamic relations. So these are the chapters we need to see under first part, which is basics. So now, learning these basics, we'll jump into the second part, which is applications. Under that, the first one is IC engines. IC engines. Followed by the second one, which is gas power cycle or gas power plant. Then followed by steam power plant. And then finally, refrigeration and air conditioning. Air conditioning. So always you should have some command on the syllabus whenever you're reading a subject, because whenever you see a gate question in the exam, you should identify first from which topic or which chapter the question is from. So that's why you should have some broad idea on the syllabus. So that's why I'm giving all this kind of divisions. The first one is basics. The first one is basics. The second one is applications. So learning these basics first, we'll see how to apply these kind of concepts and real systems. These are all real systems, which you will see very commonly in industries, sometimes in our home applications also, especially the last chapter, which is refrigeration and conditioning, which is our home application. Whereas the remaining applications are mainly, you'll see in industries and IC engines, like people using motorbikes or cars or whatever maybe. So they'll be included in IC engines. And these are all power plants where we extract power or work using these kind of fundamentals. And whenever you're reading applications, don't read something like these are not related to basics. No, that's not the correct idea. Anything, whatever you're going to read in the second part, they'll be completely correlated or linked with basics. If you don't know the basics or fundamentals, you cannot understand applications in a correct way. So I always prefer learning basics first, then only you should learn applications. That's how they're designed. That's how they are designed. And coming to the weightage perspective of the subject, you'll see around 11 to 12 marks. Very important. Coming to the weightage of the subject, thermodynamics and its applications, in terms of gate, you will see as 11 to 12 marks. So which is one of the most weighted subject, I'll say, after your mathematics. The first one you will see for production, like starting from your casting to up to your industrial engineering. We call that total production. That will be around some 23 marks. That's a rule of production, and that's a weightage of production in your gate syllabus. After that, the one of the most weighted subject is mathematics, which is around 14 to 15 marks in your mathematics. Then I'll see thermodynamics and applications as the most weighted subject, which is coming around 11 to 12 marks. It's very important. If you are good at these three subjects, you are going to score 50% of your gate marks. Are you guys feeling that, everybody? Only three subjects completely. If you have good command, if you're good at all these three subjects, you're going to gain 50% of the total gate marks. But because you can count all these three subjects, you'll be coming around 50 marks. And the remaining subjects, whatever you're having, say strength of materials, heat transfer, fluid mechanics, machine design, mechanics, any other subject, kinematics of machinery or dynamics of machinery. So all these things will come separately as 50 marks. Will come around 50 marks. So there are many subjects apart from these three. So first you try to focus on these three, get confidence on these 50 marks. Then you can go for studying the remaining subjects, the remaining 50 marks. That's how I see the total GATE syllabus. Then you'll take an advantage in terms of getting the marks in the exam. So always whenever you're writing or preparing for a competitive exam, you should have some plan always. Please be careful. It's not like reading some subjects and leaving there. So you should know the weightage. Based on the weightage, you spend time on that. Get I'll say most of the marks from that subject. Then at the end, you will feel like first thing is you have qualified the exam, then you have jumped into an IT or then IIT or then the rank whatever you're desiring. Like that, you should have a plan whenever you're writing a GATE exam. So coming to the textbooks, so very important that textbooks. Number one, Thermodynamics and its applications by Moran and Shapiro. Moran and Shapiro. Or you can follow Sengen. Thermodynamics and applications by Sengen. Try to follow these textbooks only. Because the people who are setting the paper, they generally refer these textbooks. That's why, I mean, that's what I observed. Like from the past previous GATE questions, you can see most of the questions are simply by changing the numbers, using the similar kind of questions they have given in the GATE questions, previous questions. That's what my observation. You just follow these textbooks while preparing for this. These topics, or you can follow the general textbook, which is PK If you are not comfortable with the above textbooks, you can follow PK But don't follow any local authors on that, because they'll give you a lot of misconceptions in terms of understanding the things. Better to follow these textbooks only. My preference is Moran, Shapiro, and Sengen. This is what is my preference. Both are similar in terms of giving the knowledge or the content. A PK is it's like a copy of these things in an Indian version. That's it. A PK is a professor from IIT Kharagpur. It's a copy of these textbooks in Indian version. That means he has done done a good work in writing the textbooks. Just the same. Similar to the previous textbooks, but in terms of Indian perspective, Indian English language. And you can follow some NPTEL videos of this subject. NPTEL by Professor S.K. Som or Professor Suman Chakravarti. These are from IIT Kharagpur. You can follow any of these videos. Professor S.K. Som or Professor Suman Chakravarti. I think Professor Suman Chakravarti videos are recent videos. I think last year videos. So SK Som was like very, it was like around 2008 or 9 videos. But both are very good professors in this area, thermodynamics and applications. Their research areas are this. You can follow their videos if you have any queries apart from your class. So any doubt in this syllabus and the textbooks and all? Everybody clear?
Yes, sir.
Yes, thank you. So with this understanding, let us go for basics first. Let us try to learn the basics. The first part, whatever I told already, we'll completely focus on basics. Then we'll see in the second half of your thermodynamics as applications. But please be careful. Basics are very, very, very important things. If you are good at basics, you can play with applications like anything, or you can design, you can find some new kind of applications on your way. That's the importance of basics. So always try to get very good confidence on these basics. Chapters under basics. In that perspective, let us jump into the first chapter, which is fundamentals. Let us go to the first chapter. The first part I'll write here, which is basics. Basics of thermodynamics. In that, I'll go for the first chapter, which is fundamentals. So what the importance of this chapter means, let us assume that we don't know anything, we don't know any term also regarding thermodynamics. In that perspective, we'll start this chapter. We'll learn how to talk about thermodynamics. Like whenever you go to an industry, people use some technical terms whenever they are describing some kind of system or whatever it may be. We'll learn those kind of technical terms under this chapter. Then we'll use those kind of terms when you're reading the upcoming chapters. That's the advantage of this chapter. So basically, you're going to learn some techniques or technical terms, how to talk about thermodynamics or how to deal with thermodynamics problem. So before going for the actual fundamentals, so we want to ask a question: what is the purpose of thermodynamics? Why you want to study thermodynamics? Or what you are going to learn under thermodynamics? Basically. Anybody? Any idea? What's the prime motto of this subject called thermodynamics? Anybody? Come on, man. As engineer, you should know, because most of your practical applications will be on thermodynamics.
Studying about the heat flow and its properties, sir.
Studying about heat flow and its properties. Only heat flow? You want to talk about more on heat flow only in this subject? Or any other?
And its surroundings, environment, matter.
No, you are giving all the terms, whatever you have seen in your thermodynamics class. That's not the way. Any other? What you said, half of your information is correct, but I want in-depth requirement why you want to study thermodynamics. Anybody? Yeah. So I'll see the subject as something like this. We want to learn here two important things. One is, please be careful. One is, we want to know, we want to do calculations, how to convert one form of energy into another form. So basically, we want to study different kinds of energy conversions. It's very similar to your mechanics. In mechanics also we deal the same kind of things. Like you might have done conversion of one form of energy into another form. But in thermodynamics, we don't take mechanical energies into considerations. What we deal here is thermal energies. The energies, whatever you're talking here, they're completely focused on thermal energies. There's a term called total energy. That deals with both thermal energy plus mechanical energy. But in this subject called thermodynamics, we completely focus on thermal energy. Very important. So how to convert one form of energy into another form. So if you know this conversion or calculations, first part of thermodynamics is over. If you have understood very clearly how to deal with these kind of conversions, using some kind of a technical term called a system. So we use some kind of system to do this job. So job means converting one form of energy into another form. So especially thermal energies. Then the first part of thermodynamics is over. A second part here under the same thermodynamics. So during these energy conversions, you will see the job whatever was doing this energy conversion was system. That's what I referred. The properties of the system will change. The properties of the system will change. So you should calculate, or you should be in a position to calculate what kind of properties of the system's state, property calculations. Property calculations. So you should calculate two things. One is energy conversions, one form of energy to another form. Number one. Number two, if you are able to calculate the property values of the same body or system, whatever is doing its job, if you are able to do that calculation called property calculations, then the role of thermodynamics, or the one, or whatever the information that you want to read in thermodynamics will be over. That's the main goal of the entire syllabus. Slowly we'll build this concepts, like first we'll see how to convert one form of energy to another form using some kind of system. So learning that, you'll see during this conversion, you will clearly observe like there is a change in property. A property can be, I'll give some list of properties just to get a feel. A property can be a pressure, P. A property can be a temperature of your system, T. A property can be a volume of your system. If it is a flexible system, you will see some change in volume during your conversion of energy. So we basically deal with these kind of properties. You can have many like enthalpy, internal energy, entropy. So there are many properties, but we'll slowly introduce these properties. But mainly we focus in thermodynamics on these properties like pressure, temperature, and volume. So why? Because we smartly, what we do in the later sessions of the thermodynamics class, will bring in some correlations or some equations between these properties. That means if I know, suppose say pressure, temperature, and volume for a given problem, I am in a position to solve for any property calculation. That's how the equations we derive in the upcoming classes. Are you guys clear what I'm telling you? So that's why we mainly focus on the first three important properties, which is pressure, temperature, and volume. Among these three also, if you take some kind of assumptions, only two are enough. That also we'll see later. Are you guys clear what I'm telling you? Understood? So any other property that you want to name after this PTV, we assume that we are going to derive some correlation. We assume that we are going to derive some kind of correlations or equations, so that if I know these three, pressure, temperature, and volume, you can solve for any other property that you are going to name under thermodynamics. So these kind of equations or the conversions also will read under these property calculations, especially under thermodynamics. So what's the use of these property calculations means is basically at the end of the session of your thermodynamics, what you'll do will correlate all these energies, all these energy conversions, whatever you're talking in the first part, will be completely linked to your property values. This is how we'll do a smart job. Whatever you are going to read, energy conversions, will do a smart job saying that any energy that you are interested will write into a form like property values. That means if I know the property value, I can calculate the required energy calculations, whatever you want. Understood? Clear? Everybody? Understood the main importance of thermodynamics? What do you want to read?
Yes, sir.
Yeah. So if I know these kind of calculations, like energy calculations or the property calculation, then I will be in a position to design the things, to make our systems to work. We'll see some kind of systems or applications later, some kind of applications like whatever I have given, IC engines or steam power plant or gas power plant, whatever may be, we'll try to understand how these applications work using these kind of calculations. That's a broad story about your thermodynamics. Knowing your first part like energy conversions, knowing the second part like property calculations, then we'll slowly develop some kind of equations between these energy and your property calculations. Then we'll jump into applications. That's the main job of your thermodynamics. Any questions? Understood the importance? Like at every part of your thermodynamics, you should check these points, whether you know the different kinds of energy conversions, Number two, whether you know the property calculations for to calculate your energy conversions. If you know these things, we'll jump into a second part like applications. That's what we do at every point. That's what we do at every point. Is it clear? Okay. So I'll give a standard statement what you will find in textbooks. What you will find in textbooks for thermodynamics. What is that means? It is the science of energy transfer. I'm just giving a formal statement. It is a science of energy transfer and its effects on properties. This is a formal definition of thermodynamics you will see in any textbook, whatever you refer. This is a formal definition, but I have split it into some kind of terms so that you can understand very easily. It is a science of energy transfer and its effects on your properties. So basically, you are seeing the same kind of words here. One is energy, the second one is properties. So you are means under thermodynamics, you are basically concentrated on energy and properties. How to deal these two types of quantities. So if you know how to deal these two, the thermodynamics will be over. Is it clear? Everybody understood? Okay. So please focus on this chart, whatever I have given here. Very important. So we'll be checking always at at the end of every chapter, we'll checking these points at this chart. So whether these things are getting over or not. If it is over, we close our thermodynamics. Please focus on this. This is a broad view of your thermodynamics. This is how you need to see a thermodynamics syllabus or the chapter. So this is a very important role as an engineer. You guys are mechanical engineers, so you should know why you want to read a thermodynamics being a mechanical engineer. And one more thing I want to specify here, the subject is not only important for mechanical, but also important for chemical, but also important for aerospace, but also important for material science people. So most of your engineering departments, whatever you see, they read thermodynamics as a very important course because anywhere, any engineer who want to play with conversions of your thermal energies and their property values, if they want to know, they should know thermodynamics. Any system if they are designing or want to invent or want to claim that they are going to uh, uh, design a new kind of system which works on these thermodynamics principles means they should know these kind of parameters like energy transfer, and the second thing is property calculation. So any department like your the one whatever I have named, they're all type of engineers like mechanical. They also want to work with different kinds of systems in their departments. So therefore, this thermodynamics is also a very important subject for those engineers also, not only for mechanical, not only for mechanical. It's very important. If you want, you can see their syllabus sheet also under the GATE exam. You will see thermodynamics also as an important syllabus for them also. So coming to our fundamentals, so understanding why you want to read thermodynamics. After understanding why you want to thermodynamics, let us jump into our important term under fundamentals. The first term that you want to see here is a system. A system. So now you guys have to tell me what is meant by system. Anybody? What is meant by system? Come on. Anybody has any idea on this? What is meant by system? Surendra, Ashwant, Suraj. What is meant by system? Okay, let me give you the definition of system first. Loosely speaking, a system is a one. So in this entire universe, you'll try to focus on a certain region in this entire universe for your study. You just focus on that. You don't want to see what is happening in the remaining part of that region. Whatever the focus you kept on a given certain region is called a system. Say, so this is what is your universe supposed to say. This is what is your universe supposed to say. I'm just giving a box. Just giving a box. So this is what is your universe supposed to say. This is what is your universe supposed to say. In this entire universe, in this entire universe, this entire universe will just focus on a certain region, a small space, whether it is small or big depending on the type of engineer or the people who is studying that problem. He can take a bigger region, he can take a smaller region depending on its their requirement. But in this entire universe we are just focusing on a certain region and a certain region by giving with some kind of dividing line, by giving with some kind or specifying with some kind of this dividing line is very important. To what extent you want to study, that is very important. It's not like simply you are seeing here and saying that I don't want to bother here and all. No, you need to give a clear dividing line, a distinct line, so that your system is separated or clearly defined. This is what is your system. So these are region where we are going to focus for your study. We are going to focus for our study. So this region is called a system. This region is called a system, and a line which tells us a clear distinction between your system and the remaining part. And the remaining part is called as boundary. Is called as boundary. Is called as boundary. And this boundary will divide this entire universe into two parts. One is the region which is under your focus, the other one which is left, in your universe apart from your system. That is what is called as surroundings. These are the technical terms we use in this chapter. Please be careful. Please be careful. Is it clear? Everybody understood? In this entire universe, we are going to focus on a small region, a certain region for your interest, for your study. So that region of concentration or focus is called a system. Is called a system. A line or a curve which clearly means divide your universe into two halves. One is your focus, the other one is left in the universe. That line or the dividing line is called as boundary. A boundary. And summing up of the system and surroundings is very clearly, you can say it as a universe. We can say it as universe. Any questions? Any questions? Understood what is member system? These are very important. Please be careful. The fundamentals, whatever you're talking, this will not leave at all when you are learning the entire thermodynamics. Whether it is a basics or fundamentals, you need to play every day with these kind of words like system, surroundings, boundary, universe. Very important. Very, very important. So whenever you see a problem, first primary step in solving the problem is these kind of things. After reading the question, you should identify what is system in that problem and what is the boundary you should take to solve that problem and what is the surroundings for the problem. So if you're able to define this, a first job or first part of your solving the question will be over. So always I do this kind of exercise. You guys also means uh, um, from now onwards you should go in terms of some kind of tradition in solving the thermodynamics problem, something like this. Then only at the end you will feel like you have a good command on your thermodynamics subject. So always try to prefer this kind of what you say this kind of formal things, this kind of writings in your solving problems also. During your solving problems also. Is it okay? Clear? So now let me give you a formal definition. Like whatever I told is like informal, how you see a system or how you see a surroundings in reality. Let me give you a formal definition. So if I go for a formal definition now, a system is defined as a region a region in space or universe, in space or universe, on which the study is focused, or concentrated. This is a formal definition you will see in any textbook. It's a region in space on which the study is focused or concentrated is called as your system. So anything external to this is called as surroundings. So this is what is system. So if you go for the formal definition for surroundings, anything external to system is called as surroundings. And the other one is our boundary. How you define a boundary now? Anybody?
A layer
on.
separating between the system and the surroundings.
Very good, fantastic. A separation between system and surroundings. System and surroundings. System and surroundings is known as boundary. Is known as boundary. And the one more term that we have seen, one is system, second one is surroundings, third one is boundary, and the fourth one we have seen in that figure is universe. So if you want to define universe, it's just addition of system and surroundings. It's called as universe. So these are very, very, very important terms which you will see very rigorously in your thermodynamics classes. Any chapter you go, whatever the syllabus I have given, any chapter you go, you will be seeing these kind of terms: a system, a surroundings, a boundary, and universe. So just to get a feel for these terms, let me give you an application. Say, to understand this statement, let me give an application. Say we have an IC engine, right? In your syllabus, we have an IC engine. So broadly, we'll study the IC engine something like this. So it's a cylinder in which you kept some gas or some fluid, whatever maybe. To avoid this gas to go out or leak, we'll provide some kind of solid material here. So technically, this is what is called as a piston, and we keep some weight on this. So now, what do you want to study in this problem? Anybody? Any idea? What do you want to study in this problem especially? Say if I'm defining a problem, something like this, what is your focus to study? That's the first question. What is your focus? Come on. I have some cylinder. I have some gas sitting here. And this is arrested. By means of providing a piston sitting on that with some kind of weight, just to avoid motion of the gas. You can assume that during this interaction, you can say that I am supplying some heat. Here. Just to get a feel for the problem. I'm just burning some fuel and dumping into some heat by using some kind of fuel burning or combustion chamber sitting outside this. whatever, you just leave about how you're supplying heat and all, you leave about that. So this is what is happening in a, suppose say. So now in this problem, in this kind of application, what do you want to study when you are supplying heat and all? What do you want to study? Come on, just as engineer, you just focus on this and tell me what you want to study. What is your interest? Or suppose what is your interest?
Pressure,
What is that? Sorry?
pressure applied.
Pressure applied. No. You now the question what I'm asking is what is your region of interest? Means basically we want to define what is the system in this problem, what is the boundary in this problem, what is the universe in this problem. Are you guys getting my question? So for defining these kind of terms in these kind of example or application, so now tell me what is your focus or concentration. That's what we have used some kind of wording to define system. So I'm using the same kind of words now in these kind of application. What is your focus to study the problem? What is your focus? Come on, man, you are having something sitting inside and you are pumping in some heat to do some kind of job. So what happens now? Come on, Anish Raj, what do you expect?
Sir, when the gas is pressurized, the heat will be produced, sir. So the system is the gas present area, sir.
Huh. Very good.
And the surrounding is the heat liberated area from the cylinder, sir.
Very good, very good. So very good, fantastic. That's what I was expecting. What about remaining people? Any modifications that you want to give for Anish's statement? Anybody? Dinesh or Deepak or Fabin? Any modifications or any suggestions that you want to add to the Anish Raj statement? Harish, Praneeth, Shiva, Suraj, Surender, Ashwant. What about Suraj?
No, sir.
Do you want to dispute Raj's statements?
No, sir.
Okay, good. So that's what whatever Raj said is correctly fine. So let me take the same statement, but I'll talk in a different way. See here. So now my job here or our job here to see what this gas will do if I supply some heat of some Q, suppose say, to this gas. Means basically what this do means it gets some energy when you supply Q, and this energy will be used in lifting the piston. Why? Because this piston is flexible. This piston can move up and down, whereas these cylinder walls cannot move. They're very rigid. That's what I use always, the term called rigid from your strength of materials or mechanics. That's what the terms, right? Rigid means which are not flexible, which won't deform. So that's what you might have used a term called rigid walls. So I'll use the same kind of wording here for this left, bottom, right. They're solid, rigid walls, whereas the top one is called as piston. The top one is called as piston with having some weight sitting over that. So when you supply some kind of heat, some value of heat to this gas, so our focus completely is on this gas. What happens to this gas? What happens to this gas when you are doing this kind of job like supplying of heat? When you're doing a job like supplying of heat, this completely focused. This is what is our complete focus. So therefore, the gas, whatever you're talking here, is our system. Very important. These kind of uh, uh, I mean, you need to define in a given question in the exam also. Are you guys clear? The one whatever you are focusing on during your experiment or during your supplying of heat, what I mean, need not be always supplying of heat. Please be careful. Just to get a feel for the problem, I have given you some supply of heat. So this what is your system. If your focus is on gas, suppose if your focus is on piston, in this particular problem, generally focus on gas. That's why I'm talking about gas system. Suppose sometimes a examiner can ask you, just focus on piston. What happens to piston and all means? What you will do? What is your system in that case? Come on, man. If the examiner asks you focus on piston, what is your system then?
Piston, sir.
Piston. That's simple. Simple answer. So if the examiner asks you to consider a focus or study your piston motion, then you should be concentrated on piston only. Then your system is complete a system. So please don't think like always systems means it should be in some fluid condition, it should be in some gaseous condition, it should be in some liquid condition and all. Need not be always. Depends on the type of problem what they are defining in the question. So that's what I want you guys to catch here. So it's not like always gas which is sitting here is your system. Need not be always. So sometimes you are focused maybe on the piston alone. So in that situation, your piston will be your system. Suppose if the question is something like consider both piston and gas as your focus or study. So what you will do your system as? What you will take your system as? Come on. Come on, man. In that situation, what is your system? If the question is something like consider a focus completely on your piston and gas, what is your system? What is your system? Come on, I want you guys to talk.
A total cylinder, sir, including
Yeah,
piston and gas.
correct. So in that situation or in that kind of problem, you should consider system as piston plus gas. So that's what. So why I'm telling all this kind of different situation means a problem can be any of these three. You should be careful of reading the question. What is your focus or what is your system? They are talking in the given problem. It's not like you take generally as gas. It's not like you take generally as piston. It's not like that. Problems can be of different varieties depending on the type of situation they're talking about. Sometimes it can be a gas, sometimes it can be a piston alone, sometimes it can be piston plus gas. Are you guys clear? So just to simplify the problem, I'm just taking a problem which is gas alone as a system. Gas alone as a system. That means we want to focus what happens to this gas whenever it is exchanging some heat, whenever it is doing some kind of work. Is it correct? Shall I call something like work done by the gas? Because it is lifting the piston. It is lifting the piston. So that means what this gas is doing? What this gas is doing? It is
Doing your work, sir.
doing a work. These kind of terms we use very commonly or very rigorously in thermodynamics. Whenever you see there is a displacement in the direction of force. That's what you might have learned in your mechanics also. So when you say a work is done means a displacement happening, a distance traveling, a displacement is a vector, a distance is a scalar. So that's the difference. Otherwise they are same. Okay, a displacement happening in the direction of force. A displacement happening in the direction of force, then we call a work has done. That is what is your F bar dot S bar. Is it correct? Just I'm recollecting the statements what you have learned under mechanics or the basics of your physics. Basics of your physics. So when here the gas whatever is sitting here is applying a pressure. In the what's the direction of pressure or pressure force? What do you expect the direction of force? Say if this is a y direction. Upward. Very good. Fantastic. So the gas whichever or whatever is sitting here is applying a force. Is applying a force on the piston walls. On the piston wall. You see here, this is the direction of force. So because of applying the force in this direction, you see once it reaches some kind of or once it exceeds the equilibrium condition, you see this piston starts to move in the direction of force. In the direction of force. So then you call a work has or was done by the gas, done by the system. So that's what your sometimes your interest. You want to know how much work was done by the gas or the system. Then you consider gas as your system. Or the question may be what is the distance traveled by the piston, or what is the potential energy associated with the piston. So these kind of questions may be asked. So in that situation, you consider piston as your system. Right, clear? So that's there are different kinds of problems which we'll see later, but here we will focus completely on our terms whatever you're seeing here, since our interest here is completely the fluid which is sitting inside the cylinder. So therefore this what is your system, this what is your system, and the dotted lines what are drawn means which is enclosing the gas is called as boundary. The dotted line is called as boundary. The dotted line is called as boundary. So anything external to this gas, like your piston, weight, cylinder walls, everything, we call them as surroundings. If I assume gas as your system, anything external to the gas is called as your surroundings. And clubbing this system and surroundings, we call them as universe. We call them as universe. Is it clear, everybody? Understood the basic statements, whatever you have learned here?
Yes,
Yes,
sir.
sir.
Yeah. So one more thing I want to add here is the boundary. How many boundaries are associated in the problem? Anybody? How many boundaries you can see here?
The 4, sir.
4. Very good. Fantastic. You can see here left, right, top, bottom. There are 4 boundaries included in the problem. Out of these 4, how many boundaries are moving in the problem?
Sir,
How many boundaries are able to move?
One boundary, sir.
Very good, very
one
good. So that
boundary.
means our boundaries can have 2 choices. One is a flexible boundary. A flexible boundary can be flexible, a boundary can be rigid. So these are possible cases. These are possible cases. These also you need to identify in a given problem. In a given problem, a boundary, whatever you're choosing, can be a flexible, which can move. A boundary cannot move also. So those kind of boundaries are rigid. Very important. Sometimes these flexible boundaries are very advantage to us. Sometimes these rigid boundaries are very advantage to us, depending on the type of problem. Depending on the type of problem. A boundaries can be flexible, a boundary can be rigid. So any questions here? Okay, if these are fine, if you want, you can take one more example. Say, I'll take a coffee in a cup, suppose, say, a coffee in a cup. So this is a cup that you are talking about. So in which we have added some coffee. These are exercise that we do in the morning. Let us take the same example. So what I'll do after preparing a coffee, you add some sugar in this. You add some sugar in this, and you want to make this coffee to come to a comfortable temperature so that you can drink. So to do that, what do? You just keep some kind of spoon or stirrer in this coffee by adding some sugar, and you want to stir this. So this is what is your coffee. Is it right? So to by using a spoon, you are supplying some work. You are supplying some work. Is it right? Yes or no? So what is your system now in studying this or to making this coffee to come to a comfortable temperature to drink or whatever maybe? So what is your system? What is your focus?
Coffee, sir.
Coffee. Very good. Fantastic. So now if you take a system boundary, let me draw a system boundary, something like this. So in this particular problem, coffee is your boundary. See how I'm drawing the boundary. That's very important. You should enclose only coffee. You should not talk about a stirrer or the spoon, whatever you have kept inside your coffee to for stirring. That is not that is not included in your system. So don't take something like a horizontal line. Some people draw here. Don't do that. So you should take a boundary something like which is included only for coffee. Which is included only for coffee. So this coffee is your system. This is what is your system, and which the line whatever you're drawn is the boundary. And what is your surroundings in this problem? In this problem, what is your surroundings?
The room, sir.
A room or generally you don't talk about room and that. The surroundings is your stirrer. What you said is correct only, but generally speaking, we talk stirrer as your surroundings. And this coffee plus stirrer is called as universe. This coffee plus surroundings, This coffee plus your stirrer is called as your surroundings. Similar to your previous problem. Similar to your previous problem. But the coffee and all, whatever I'm talking here, you will see as an industrial application, you will see as an industrial application something like mixing of two fluids. Is it right? We'll have some hot fluid, you'll have some cold fluid, you want to mix. Is it correct, everybody? You can see that application industries, right? Yes or no? You want to mix those two fluids and you dump into some kind of cylinder and you do some kind of stirring operation. So generally this kind of stirrer, whatever you are doing in a coffee kind of application, in a real industrial application, this is connected to a motor. This is connected to a motor. You switch on the motor and see the stirrer will be rotating and it is making your fluids to mix. Yes or no? Are you guys correlating the things with your industrial application?
Yes, sir.
Huh. So in reality, this stirrer, whatever you're talking, will be connected to a motor. You switch on the electrical energy, so that electrical energy will try to rotate the stirrer with some kind of RPM by supplying some kind of power input, and that stirrer will rotate and make your fluids to mix. Or some kind of molten liquid metal from your casting application or a welding application, whatever may be, you need some kind of molten metal. So there also again the molten metal, whatever is sitting here, if you want to stir that, you will do the same kind of job, the same kind of application. So these are all real industrial application. So just to understand very easily, use some kind of coffee application, whatever you see in our kitchen or in our home. So, so is it clear how to identify a system, boundary, and surroundings? Anybody, any doubts? Or shall we go to the next topic? So why I'm spending a lot of time here? This is the very important statement that any problem you see in thermodynamics, very important. Without this, you cannot study thermodynamics. These statements, whatever I have written with red or yellow or white, whatever may be in this slide, every statement is very important in understanding thermodynamics or in solving problems. So whenever you read a question in thermodynamics, first thing you should identify is what is the system that they're talking about, what is the surroundings that you need to take care, what is the boundary that you want to include. So these kind of statements, if you are comfortable, then the first part of your solving problem will be over. Okay, if it is clear, let us go for defining different types of systems. The next one is types of systems.
Sir, I have a question, sir.
Yes.
Sir, in the previous example, you said that if they didn't specify any system, sir, focused or concentrated, how can we find what is the system is, sir?
No, they'll define definitely. Without that, we cannot solve. They'll not use a word something like focus or concentrated or system something like. They don't use these kind of words. The question runs completely talking about something. Say if the question is something like what is the amount of heat added to the gas, or what is the amount of work done by the gas. These are the types of questions. What is the amount of internal energy change for the given gas which is sitting inside the cylinder? Are you guys clear?
Okay,
Nowhere
sir.
they talk about take this as system, take this as your focus, take this as your concentration. They don't talk something like this. Very rarely you see those kind of terms. In the exam or in the question, any question you take, a question will be something like this. In an indirect way, what is that means? Say you have a fluid which is sitting inside the cylinder. Now I'm adding some heat and it is doing some kind of work. A question will be something like this. What is the amount of heat added to the gas? Or what is the amount of work done by the gas? It's indirect saying that assume the gas which is sitting inside the cylinder as your system. Is it right?
Yes, sir.
So that's a way of questioning. It's not like defining a system in the question itself, asking question. That's not the deal. Why? Because you should know that comes with practice. Actually speaking, you should know how to define a system for the kind of statements that they are using in the question. This kind of relation has to be there. When you're reading the question, you should know what kind of system is good for solving a kind of problem that you're talking about. Clear?
Yes, sir. Understood, sir.
Yeah. So that will come through practice. We will see some problems. Later you will come to know how to identify all these kind of things. Fine. So now coming to our types of systems. Types of systems. So broadly speaking, in your entire thermodynamics, we'll see three kinds of systems. We'll see three kinds of systems. One is a closed system problem. Closed system. Number two, open system. Number two, open system. Number three, isolated system. Very important. You will see the thermodynamics also like the same way. The entire thermodynamics will come to know. I'll divide something like this only. A system can be a closed system. A system can be an open system. A system can be an isolated system. Don't think like closed means it's a closed one. Open means open one. Don't think like that. I have seen a lot of students talking something like that. No, it's not like that. there's a different definition for these kind of words. But it's very important. You should identify what kind of system they're talking in a given question or given kind of application. It's very important. So coming to the first one, which is a closed system. So we want to define, suppose say we want to see a kind of application, what is meant by closed system. What is meant by a closed system? Anybody, any questions? I mean, sorry, it's not question. Any idea on this
A
closed system?
system where only energy can be exchanged but not mass.
Very good, fantastic. So you take any system. So system means there's a statement for the system. So you take any study, whichever your interest, whichever your focus. In that study, you see only energy interactions with the surroundings. You see only energy interaction with the surroundings, no mass interaction, no mass interaction. Those kind of systems are technically called as closed systems. Those kind of systems are called as technically closed systems. A system in which only energy interaction happens. Only energy interaction happens, but not mass interaction or mass transfer, is called as closed system. This is a formal definition. Is called as closed system. Is called as closed system. So that means you have a system. You see only energy interactions. Say I'll write something like delta E not equal to 0. That means you will be having some energy interaction with the system and surroundings, but you don't see any mass interaction. Delta M equal to 0. You'll see that mass of the system is remaining same during this interaction. Mass, whatever you have taken before energy interaction, after energy interaction, you will see the mass is fixed. Mass of the gas, or the fluid, or the solid, whatever sitting inside the system or inside your boundary is fixed. So those kind of systems are called as closed systems. Those kind of systems are called as closed systems. This is what is your system. A good example for this kind of problem is the one whatever I talked already. So what about these two examples? What's the mass of the gas? Suppose you are talking here. Whether it will change? Come on. No, right? Say you have taken some 1 kg of mass of gas, suppose before supplying of heat. You expect the same 1 kg because we are not allowing the gas to leak from any of the spaces. You are fixing completely, assuming that there is no leak in the problem. Say if you're having some leak through the cylinder wall or from this space between piston and cylinder, you expect some gas to be left from the cylinder. But we are not doing those kind of things here. We are assuming that it's perfectly leak-proof. It's perfectly leak-proof. So that the mass of the gas, whatever you're talking here, before your energy interactions and after energy interaction, you're seeing the same mass. I'm talking about mass. So mass means density into volume. In this problem, mass means density into volume. So mass is fixed, but when you supply heat, when the piston moves up and down, you see what are the changes? What's the change mainly? Say when the piston moves up, what do you see?
Volume increases.
Volume increase. Very good. The volume can change, which will be resulted in density adjustments according to the volume, and totally you will see the mass remaining constant. It's not like only volume is changing here. If your volume is changing, you will see there is a density change also. Correspondingly, the product has to come out as same, which is mass we are defining here. When the volume decreases, density has to increase because the gas molecules are coming very close now when the volume is decreasing. So you expect density more. And vice versa. What is that? If the volume is increasing, you see the molecules are going very far, you expect the density coming down, but the product will be same. So these kind of systems are again called as closed systems. I'll write here a statement called closed. A closed system. A closed system. So what do you expect this example? What about
Open
this
system. Open system.
Need not be. Here I'm assuming we are not leaving any coffee, right? The coffee of the mass, mass of your coffee before stirring and after stirring will be same, right? We're
Almost.
not.
Oh, okay.
Yeah. It's not like a coffee is suddenly moving out of your space. It's not like that. You
Yes,
don't
sir.
want to do that. Otherwise, how can you drink a coffee? Here also the problem is a closed system. Only thing is you are having a gas, so therefore there is a possibility of leaving the gas if you are not having a piston. That's how a gas behaves. But that will not be a situation with the liquid. That will not be a situation with the liquid. If you provide some enough height to the cup, enough height to the cup, when you are stirring, you will not lose any coffee. But suppose if you are taking a full glass of coffee and when you try to stir, what will happen? What will happen in that situation? Come on, man. In that situation, what will happen? If you take suppose a cup with full of coffee, then you start stirring, what will happen? Generally,
The coffee will overflow, sir.
yeah, very good. So in that situation, you see both mass transfer as well as energy transfer. But that is, we don't want to do that kind of job in a home also. Why? Because we don't want to spill the coffee. So we make sure always a coffee, whatever you taking in a cup. At least you will feel like coffee has to be taken lesser than your coffee, means the cup whatever you are taking, or you take a cup with having enough height or enough volume so that the amount of coffee that you want to drink will be occupied in that space. So these are the two possible ways. So basically what I want to tell here is, you see here in these problems there is energy interaction happening. In this problem the energy interaction is work input. By rotating the stirrer you are doing some work. And during this energy interaction you see the mass of the coffee is fixed, and you can have some heat interaction with the surroundings. This is a possible case. That's how a coffee temperature will come down. Then you will be comfortable in drinking a coffee. So there is energy interaction in the form of work and heat. But there is no mass interaction with the surroundings. The mass of your coffee before stirring and after stirring, or before energy interaction or after energy interaction, is almost same. We assume this as a closed system problem. Similarly here also, a gas which is sitting here is having the same mass during lifting of the piston or after lifting the piston, during supplying of heat. You see the same mass of the gas. So again this example comes under closed system. These are very good examples for closed systems, which you will be seeing very rigorously in problems also. That's why I'm introducing these two problems. Very important. Please be careful. Any problem that you see in the upcoming classes, most of your 99.99% problems will be completely associated with these kind of problems, mainly under closed system. So whenever you see a piston cylinder problem, a stirring kind of problem, you assume the problem as closed system. Mostly. There is no leak of gas in this. There is no what do you say, spilling of coffee or fluid, whatever is sitting here. I'm talking coffee here, but in the subject perspective, you don't see coffee. We'll see some kind of fluid. We'll see some kind of fluid. Any questions in this understanding closed system? So a closed system means with only energy interaction, no mass interaction. These kind of systems are called as closed system problems. And the very good examples are your piston cylinder example, a piston cylinder, and a cylinder with a stirrer. Cylinder with a stirrer, very important, etc. You have many, but these are the major for your industrial applications. For your industrial applications. So coming to the next one, which is open system. So how you guys define open system now? Understanding closed system.
Both
System
mass
where
and energy
both
interaction takes
mass
place,
and
sir.
System where
both mass and energy interaction takes.
yes, correct, very good. So now you are allowing both to interact. Not only energy, you expect mass also to interact with the surroundings. So those kind of systems are called as open system problems. So if you write a formal definition, a system in which both energy and mass interaction happens is called as open system. It's very important. You see both energy and mass interactions. So you have a system, some system, so in which you see both energy interactions and mass interactions. They're called as open systems. So I can say from my experience, most of your practical examples or industrial applications, you will see open system problems. You will see open system problems. Very limited applications you will see on closed system problems. That's very important. Very limited applications you will see on closed system problems. Mostly the applications will be on open system. Even in the exams also, that's why they want to test you mostly on open system. It's not like they don't ask any question closed. It will be, but the examples are very limited, especially for mechanical industrial applications. What I'm talking about, they're very limited, like the examples what I have given. But open system have many examples or many applications. Let us see that. The examples or applications for open system. Number one, turbine. Turbine. Number two, you can have a compressor. Number three, you can have a pump. Number four, you can have a blower. Number five, you can have a fan. Number six, you can have a nozzle. I'll explain you all these things. Number seven, you can have a heat exchanger. Any other that you want to add? Number eight, a combustion chamber. Come on, if you guys want to add something, you can add. These are all practical industrial applications. You have many, but these are common examples. How many? These are common examples where you see both energy and mass interactions. They are called as open systems. So let me take some specific examples. Let me talk about first, suppose a turbine. So if I take a turbine, suppose this is how we generally represent a turbine in thermodynamics. This is a turbine. into which generally in a real application, you will be having some fluid coming in and going out. So now tell me what is your system. I'm not talking about closed or open. Just tell me what is your system or what is your focus or study or concentration, whatever, any term that you use. What is your focus? Come on, tell me. What is your focus?
Turbine.
Turbine, very good. So that means I need to draw a region now enclosing your turbine space. So this, what is our interest? I'm just drawing some boundary. This is what is your interest. The red line is your interest. And some fluid is coming into the region, in this region. It is doing something and going out. Is it right? And during this fluid coming in and going out, you will see some kind of work coming out, work done, that we represent as work done by the turbine. Maybe sometimes if the fluid is at a very high temperature, you will see some energy in the form of heat is leaving from the turbine because of assuming that your turbine is at a higher temperature compared to your surroundings, which is next to your turbine, Are you guys clear? So this fluid, whatever is coming in, may be a gaseous fluid, or maybe a steam. You can have a gaseous fluid, completely gas. That is what is your gas power plant says. You send in some gas, some air or some kind of gas, and rotate the turbine, get the work out from the turbine. So that is what is called as gaseous turbine or gas power plant. You can have, instead of gas, you can have a steam. Steam means a water in vapor form. Is it correct? Yes or no?
Yes,
Yes,
sir.
sir.
Water in vapor form, you are sending with a very high energy steam and you're trying to rotate the turbine. So that is what is happening in your steam power plant. You expect the same kind of job to be done by the same turbine. So a fluid is coming in, is it right? That's what you're seeing here. A fluid in the form of gas or steam is coming in with some energy, coming in and rotating the turbine and going out. That means you're having a mass interaction as well as energy interactions. So these kind of examples comes under open systems. Very important. So please be careful. In the previous problem, like closed system, you see there is a volume change to a given system. You can have a volume change, but mass is constant. In these problems like closed systems, you see volume can change. That depends on the problem again, need not be always. Volume can change. That's why I'm using called can change, but mass is constant. Mass is fixed. This is a very important statement from closed or conclusion from closed system problems. Whereas in a problem like open, what about your volume? What about your volume of a system?
Volume is fixed, sir.
Yes, very good. Why? Because your turbine walls, they cannot have a flexible boundaries. They cannot have a flexible surfaces. You always see in these kind of components, in these kind of applications, the walls are fixed, are rigid. So you expect always the volume, whatever you are seeing as a focus, will be always fixed. So you expect volume fixed here. Volume is fixed. Volume of your region is fixed, but mass can change. The mass of the system can change. The system mass, whatever you're seeing here, can change. So that's why we technically call these kind of problems as control volume analysis problem. Control volume analysis problem. Unlike your closed system problems. Control volume, that means volume is fixed. We take a volume here, which is fixed volume, and we do our calculations. So that's why we always use control volume analysis. And this region generally represented as CV, control volume CV. A region of your interest is represented in a kind of examples like open system as control volume. Okay, and the boundary, whatever you've taken here, is also called as, already we have defined a term called boundary, but in these kind of examples they are also called as control surface. Control surface. Control surface. Boundaries are also called as control surfaces. Okay, and here if you go to a closed system problem, this mass is fixed. That's why this is also called as control mass. This is also called as control mass problem. Control mass problem. Are you guys following what I'm telling you? Is closed system problems are also called as control mass because you are fixing the mass. Whereas in this open system, you are fixing the volume. That's why they're called as control volume problems or control volume analysis problems. Control volume analysis problems. And these boundaries are called as control surfaces. Control surfaces. So just to get a feel for one more example, let me take a very important application, which is nozzle, which is called as nozzle. Remaining all are similar. It's similar to your turbine, a little different from these examples are nozzles. So this is how a nozzle will be. This is technically called as convergent divergent nozzle. Convergent divergent nozzle. Sorry. Convergent divergent nozzle. So what's the application or what's the use of this nozzle is, you send in with a very low velocity, almost zero velocity, and you expect a very high velocity at the other end. So generally you see a number something like 500 to 1000 meter per second depending on your application. So you are sending in some gas here, some gas, maybe gas or steam depending on the problem. Okay, gas or steam depending on the problem. So gas means it's a application related to your aircraft engines. Is it correct? You'll see aircrafts given with some nozzles at the end. So they'll use the thrust developed by these nozzles or rockets. You can see the same kind of nozzles in rockets also. The purpose of these nozzles is to develop the thrust. So if there is enough thrust, then these vehicles will fly in the given direction. So that's what you might have learned in your if you guys have done something like gas dynamics course. Do you have gas dynamics course? But because in fluid mechanics we don't see much about this, because fluid dynamics mostly talks about your liquids, not on gases. But this kind of application you will see mostly in a subject called gas dynamics. I don't know whether you guys are having gas dynamics in your curriculum or not.
No,
but
sir.
that is not there in your no, I think this year they have added in your curriculum also for gate exam. In gate exam also they have added this time, particularly from this time they have added this type of syllabus also. I don't think you might have read in your normal curriculum, right? Academics, right? Yes or no? Anybody read this?
No, sir.
Yeah, but this time they have added in gate syllabus. I think your colleges has to adjust their syllabus or curriculum according to that.
No.
That will be helpful for students. From this side, this year they have added this kind of syllabus also. So that means what happens if gas moves with very high velocities, what happens to the physics and all, you should learn. So that subject is a kind of subject which is little different from your fluid mechanics, which is gas dynamics. In fluid mechanics, we talk more on liquids. we generally rarely talk about gases in fluid mechanics, but it's very important to study these gases separately. So that course is called as gas dynamics. That should be in your curriculum, where most of your aircrafts, rockets, okay, all these applications which fly with very high speeds or which move with very high speeds will be dealt. There are different terms which you should know or which you should learn. So now tell me, leave about that. Now tell me, what is your system or what is your focus in this example? Or understanding the previous problem, I'll ask a question. What is your control volume? Come on, quick. We are slowly out of time. What is your control volume? Come on, man. I've given you some solid boundaries. Now tell me, what is your system? What is your boundary? Come on, what is your boundary? What is your interest in this problem? A gas is coming in, doing something and going out. What do you want to study here? You want to enclose this gas when it is coming inside these solid surfaces as your system. Are you guys following what I am telling you? This is what is your control volume. Is it open system or closed system?
Open.
Open. Why?
Both mass and energy transfer is
Very
taking
good. That's
place.
what it's straightforward statement. You see some mass coming in, doing something and going out, and during this mass interaction, you will see some energy interaction also, some in the form of heat. Do you expect some kind of work here?
No work because
No, very
volume is
important. That's what
constant.
very important here. So always you prefer work transfers calculations in the kind of rotating devices. Whenever something is rotating or something is moving, you expect a work like the examples. Whatever I'll write, I'll give a tick mark here. You will see work transfers in turbines, compressors, pumps, blowers, fans. Yes or no? In these examples, you will see something is rotating. So then you will see some kind of work transfers, maybe work input, maybe work out, whatever, depending on the application. But you don't see any work heat interactions will be there. No work interaction in these kind of examples like nozzles. You don't see any work interaction, heat exchangers, and combustion chambers. These are very important to differentiate. So you don't always expect work transfers in a given problem. That depends on the problem. It's not always. Only in these tick marked applications, you will see work transfers. In these cross-mark applications, no work is associated in these problems. You are not going to produce any work or you are not going to supply any work in this because their job is different. The purpose of these applications are different. The purpose of heat exchanger combustion chamber is you want to supply heat, that's it. You don't want to do any work in those kind of applications. And the purpose of nozzle is to increase its velocity, to accelerate a fluid. That's the purpose of the nozzle. So that's why you don't do any work interaction in these problems. Are you guys clear? Understood the examples of open system? So like that you have many under open systems. So that's why you spend more time on these open systems. More time on these open systems because of having large number of applications. Then the last type of system is isolated, which we'll discuss tomorrow. Is it fine? We are at 8:30.
Yes, sir.
Anybody, any questions here?
Yes.
Everybody comfortable to follow? Or do you want to suggest something to do some kind of things? Fine?
Yes, sir. Fine, sir.
Yeah. Thank you. We'll stop here. We'll meet tomorrow at the same time. See you. Bye.
Yes, sir. Thank you, sir.
Thank you, sir.
Bye. Bye.